All right, let's dive in. Today we are talking about one of the most powerful ideas in all of science, the universe as seen by Isaac Newton. For hundreds of years, his laws gave us this incredible picture of a grand, predictable, clockwork cosmos. So let's wind it up and see exactly how it ticks.
But before you can describe how anything moves, you have to answer what sounds like a simple question. The Earth is spinning on its axis, right? And it's orbiting the Sun. And the Sun is whipping through the galaxy, you get the idea. So with everything in motion, how do we measure anything?
See, this was the fundamental problem Newton had to crack. Before he could even think about writing down his famous laws of motion, he had to figure out what the stage looked like, the arena where all this cosmic action takes place.
And Newton's solution? Well, it was as bold as it was brilliant. He basically proposed that underneath all the chaos, there's a fixed, absolute arena for everything.
Here's what he imagined. He pictured this rigid, totally invisible 3D grid filling all of space. He called it absolute space. It's the ultimate stage, and it doesn't move, ever. And ticking along with it is a universal master clock, what he called absolute time, clicking away at the exact same rate for everybody, everywhere, no matter what. This was it. This was his unchanging backdrop for reality.
Okay, so we've got our absolute stage, but there's a catch. How we, the observers, see all this motion, well, that still matters a lot. And Newton realized that to see the laws of physics in their purest, simplest form, you have to be in a very special kind of place.
He called these special places inertial frames. You can think of them as the universe's quiet rooms. Imagine you're in a spaceship just gliding through the vacuum of deep space. The engines are off, you're not turning, you're not speeding up or slowing down. If you take out a pen and just let it go, it'll either just float right there or drift away in a perfectly straight line. That is an inertial frame. It's the perfect, calm laboratory for doing physics.
And this visual really nails the difference. On the left, you've got that smooth-moving lab, an inertial frame. Everything inside behaves predictably. But the lab on the right, it's tumbling and spinning. Inside there, things would look like they're flying around for no reason at all. That's a non-inertial frame, and it's where the laws of physics start to look really weird and complicated.
So here's the key takeaway. Newton's famous laws, F equals ma, all that stuff, they are written specifically for these calm, non-accelerating viewpoints. In an inertial frame, the universe makes simple, elegant sense. But in a non-inertial frame, you have to start inventing things like fictitious forces. You know, that feeling that pushes you against the door when your car takes a sharp turn, just to get the math to work out. And this leads to an absolutely profound idea. The laws of physics are democratic. It doesn't matter if your quiet room, your inertial frame, is here on Earth or on a spaceship cruising at a constant 1,000,000 miles an hour towards another galaxy. If you do the same experiment, you will get the exact same result. The laws of nature don't play favorites.
Okay, so we've got our absolute stage and we've got our special quiet rooms to view it from. Now, let's bring in the star of the show, the main actor in Newton's cosmic play, gravity.
And there it is. Seriously, this is one of the most successful equations ever written down. What it says is actually pretty simple. Every single thing with mass in the universe is pulling on every other thing with mass. How strong is that pull? Well, it just depends on how much mass they have and how far apart they are. Simple as that. This one little rule governs everything from an apple falling from a tree to the planets orbiting the sun.
And check this out. This is just beautiful. On the left, you've got the math for gravity. On the right, the math for the electric force. Do you see it? The structure, the form of the equations is almost identical. It's like nature found a design it really liked and decided to just use it again. It's a huge hint that there are these deep, elegant patterns woven into the fabric of the cosmos.
But there's always a but, isn't there? Even in this magnificent, perfect-looking clockwork system, there was a tiny, nagging crack. A deep mystery that Newton himself saw but couldn't explain. And it all comes down to the very idea of what mass is.
Let's get our terms straight. First, there's what we call inertial mass. The best way to think about this is as an object's stubbornness. It's a measure of how much it resists being pushed around. A bowling ball has a lot of inertial mass. A ping pong ball has very, very little. Simple.
Then you've got something called gravitational mass. Now, conceptually, this is a totally different thing. This isn't about resisting motion, it's about causing motion. It's the property that determines how strongly gravity pulls on an object. It's kind of like an object's gravitational charge.
And right here, this is the puzzle. Why on earth should an object's stubbornness have anything to do with its gravitational attraction?
I mean, really think about it. One is about resisting any kind of push, and the other is about how it responds to this one very specific pull, gravity. There's no obvious reason they should be connected at all.
And yet, they are. This is the experimental bombshell. It's the reason that if you go to the moon and drop a hammer and a feather, they hit the ground at the exact same time. The hammer has way more stubbornness, sure, but it also feels a way stronger gravitational pull. And somehow, those two effects cancel each other out perfectly.
And the only way that can be true, the only way the math works, is if an object's inertial mass is precisely, exactly equal to its gravitational mass.
I want to be really clear here. This isn't just an approximation. It's not close enough. As far as any experiment has ever been able to tell, down to the tiniest decimal place, this equality is perfect. It is one of the most precisely tested facts in all of physics. And you know who this bothered? Newton himself. To him, it was just a bizarre coincidence. He called it a truly remarkable, but ultimately random, unexplained fact about how the universe was built. He had no theory for why it should be true.
But what if it's not a coincidence? What if it's a clue, a huge clue? More than 200 years later, another physicist came along, looked at this same coincidence, and saw something else entirely. He saw it as a signpost, pointing towards a completely new understanding of gravity itself.
And that leads us to a final, mind-bending question. What if the reason everything falls in the same way isn't because they're being pulled by a force at all? What if they are all just following the straightest possible path through a cosmic stage that is itself curved and warped by mass and energy? What if gravity is the shape of space-time? Well, that's a story for another explainer.